Hello everyone. Today we will discuss about a very important topic of the radiations and the matter to be act both as waves or both as particles. This topic of dual nature of radiations and particles or means matter is included in 12th class physics curriculum. Under this topic, we will understand how radiations and matter possess both kind of behavior as waves and as particles. So, to begin with, let us recall about lights. For example, light is a kind of electromagnetic radiations. So, we have two views about the light as we have discussed in our previous classes. In the ray optics, we have discussed the phenomena of reflection, refraction, dispersion, total internal reflection, all these phenomena on the basis of Newton's theory of light, which is the ray theory of light, or it is also called as corpuscular theory of light. According to the Newton's view or Newton, the light consists of corpusculars, small groups of particles of energy, which travels along a straight line. And with this theory of Newton's, we understood the phenomena of reflection, refraction, dispersion, total internal reflection successfully as explained by the ray theory of light, right? So in Newton's view, light is a form of particle. It travels just like the corpusculars of particles which travel along the straight line. Then came the Huygens, and he pointed out that if light travels just like a straight line, then how the phenomena of interference, diffraction and polarization are shown by the light itself. We already have discussed about Huygens theory, which is wave theory of light, which considers the light to be a wave. And on the basis of this wave theory of Huygens towards light, we understood the phenomena of reflection, refraction and interference, diffraction and polarization successfully on the basis of Huygens theory of the light. This phenomena, interference, diffraction and polarization, could not be explained on the basis of considering the light to be the corpusculars of energy as suggested by Newton's theory, right? So but on the basis of Huygens wave theory, we can even understand the interference, diffraction, polarization shown by the light in addition to the reflection, refraction and other phenomena as suggested earlier. So that means the view of Huygens or acceptability of Huygens view or Huygens wave theory of light is quite wide. Okay, but still there are other phenomena which light follows, just like photoelectric effect, Compton effect, etc., Raman effect, just like those. These phenomena are such that where a particle interacts with a particle, right? So here, if we consider according to Huygens, we consider its wide acceptable, more acceptable theory, wave theory of light, then the wave theory of light will be applied to understand the phenomena of photoelectric effect, Compton effect and other effects just like Raman effect shown by the light. And we will come to know about that how this wave theory of light explains these phenomena of photoelectric effect, Compton effect, just like these. And whether this Huygens wave theory of light successfully or accurately explains these effects or not, right? So to begin with, we start with the what is light again. So light in simple form, it is a form of energy called as electromagnetic energy. According to Newton's theory, it behaves in one way, and according to Huygens, it behaves the other way as the wave. So light is a kind of wave in as viewed by the Huygens. Other types of electromagnetic energy also include the radio waves, microwaves, which we already know about them. So the very first thing here, we will try to understand how the photoelectric effect is shown by the light. To begin with, we need to discuss what a photoelectric effect is and what are the main outcomes of this photoelectric effect. We see this phenomena or this effect of photoelectric effect to be happening in a number of ways, right? In fluorescent tubes, also in solar cells, this phenomena of photoelectric effect takes place. So what is this phenomena? The phenomena of emission of electrons from mainly the metal surfaces, whenever these metal surfaces are exposed to light energy. This light energy may be in the form of X-rays, gamma rays, UV rays, or visible light, and even infrared rays of light, right? Or we can say electromagnetic radiation. And this photoelectric effect happens for the light energy, for the radiations or electromagnetic radiations having some suitable frequency. This phenomena of emission of electrons from the metal surfaces which are exposed to some light this phenomena is called as the photoelectric effect. So one thing is clear, that what photoelectric effect means. It simply means the ejection or emission of electrons from a metal surface whenever an electromagnetic radiation of some certain energy is incident on the metal surface, right? So these electrons emitted in this kind of effect or photoelectric effect, these are called as photoelectrons, and the current constituted by these photoelectrons is called as photoelectric current. This is quite simple, there is no complicated things here. Even non-metals just like liquids and gases also show the photoelectric effect, but not up to so clear extent, very limited, up to very limited extent. Okay, so what happens in case of metals? The electrons in the outermost orbit, they are very loosely bound to the nucleus, and whenever radiations of particular energy are incident on this metal surface, the electrons in the outermost orbit of these atoms present in the metal, they gain sufficient amount of energy, and now these electrons in the outermost orbit are able to overcome the attractive force of the nucleus and hence leave the atom and become free. So these electrons now are said to be emitted electrons, or we call them here as the photoelectrons. They are now free from the this metal surface. These electrons are made free from the metal, and these electrons are called as photoelectrons, are now able to draw some current, or to produce, or we can say constitute some current if they are made to do so. Similarly, there are some metals other than the alkali metals on which if visible light is incident, then no photoelectrons comes out because the light is not of sufficient amount of energy. But in case of alkali metals, whenever visible light is incident, photoelectrons are emitted out. So the phenomena is quite simple, that whenever a radiation of certain kind of energy is incident on the metal surface, the electrons are emitted out from the metal surface, called as the photoelectric effect. And this phenomena is the photoelectric effect. Like electrons are given the name photoelectrons, and the current constituted by these photoelectrons or emitted electrons, it is called as the photoelectric current. So it depends upon how much current and what kind of radiation will be able to remove the electrons or eject out the electrons from the metal surface. It will depend upon what kind of metal surface we are using, because the different metal surfaces will have different nature, right? So in what sense the nature is different, we will discuss them one by one in the coming moments. So this is the experimental setup of photoelectric effect. What is there? There is a glass tube which has one opening through which the light, or we can say radiation, is allowed to come in, and there is a cathode plate which is over which some metallic substance is coated, which can be exposed to the radiations, and there is some anode. These cathode and anode are connected through the battery. This is the driving battery. Actually it just drives the electron from cathode to anode. The cathode is connected to the negative of the battery, and anode is connected to the positive of the battery. So cathode, it is a metallic we can say plate, and anode, it is also a metallic plate, right? So there is one window from which the radiation or light can enter this experimental tube of photoelectric effect. So let us start about discussing the photoelectric effect, how this happens and what results comes out there. So when radiation of some particular energy is allowed to come and fall on this cathode, it just overcomes the attractive energy of the nucleus towards, or we can say attractive force of nucleus towards the outermost electrons, and these electrons with this energy of the incident radiation, they become free and come out of this cathode. Now where these free electrons will go? With the application of this potential, they will be directed towards the anode. If we increase this potential, the electrons will move quite fastly towards the anode, right? So the electrons which reach the anode, now they constitute some current in microamperes, of course. The current constituted by these electrons called as photoelectrons, this current is called as photocurrent. So now we will discuss some we can say results which appear or observation that has been made in this experiment of photoelectric effect. So very first thing that has been observed is that the effect of incident light on the photoelectric current or photocurrent. So it has been observed whenever the radiations of different intensities are used, which all of them have the same frequency. So frequency is not different, only the intensity of the radiation is different. So with the increase in the intensity, the photocurrent increases. That simply means more is the intensity, more will be the emission of electrons from the metal surfaces. More number of electrons will be emitted out, and those more number of electrons will constitute more amount of photocurrent. So the effect of intensity of the incident radiation is that more is the intensity, more intense the radiation is, more is the emission of electrons, and hence more is the photocurrent. The second observation is that the effect of potential on the photoelectric current. So the observation is that if we keep the intensity as well as frequency of a particular radiation fixed, then how the photocurrent changes with this potential which is applied here, this potential. So what this potential does? This potential makes these electrons move from cathode, released electrons from cathode towards anode, and with this movement the photocurrent is constituted. So we are keeping all other factors just like frequency and intensity of the radiation to be same. We are making use of the same radiation. What thing we are here changing? This potential. If we increase this potential, electron will be pushed towards the anode with more amount of energy, or we can say force. With this, if electrons move towards anode with more amount of force, means they will move fastly, they will constitute more amount of photocurrent. So this can be shown here. So it can be seen here that when we increase the potential of anode, the photocurrent goes on increasing, right? It goes on increasing till it becomes maximum and increase no more. So it becomes constant at a particular value of the potential. So this constant value of photocurrent, it is called as the saturation current. So first graph for L1 here is the intensity of the first radiation, and if we increase the intensity, we will get the saturation current to be a higher bit. Of course, as we have discussed here. Here we have to understand only the effect of potential. So more is the potential, more will be the value of current, or we can say saturation current. So that means the potential of the anode also decides the value of photocurrent. And how it decides? More is the value of anode potential, more will be the photocurrent produced there. Here we need to understand one more thing here is that when potential of anode is 0, even then there is some value of current. That simply means even when potential is 0, even then there are some electrons which can move from cathode to anode. So hence they constitute some amount of current, right? So in order, we want to stop all the electrons which are moving from cathode to anode. If we are willing to stop them, we have to apply the negative potential, right? We have to connect cathode with the positive terminal and anode with a negative terminal, so that the electrons are prohibited or prevented from coming to the anode, right? So for this negative potential which we apply in order to stop the electron from reaching the anode, so that photocurrent becomes zero. So this negative potential applied so as to stop the photocurrents, or we can say photoelectrons, in reaching the anode and hence making the photocurrent zero. This negative potential applied, it is called as the stopping potential. So it becomes zero at a particular value of this negative potential. So this particular value also depends upon the nature of the radiation we are making use of, right? So this negative potential, it is called as stopping potential because it stops the electrons from reaching the anode and hence make the photocurrent to be zero. It is also called as the cut-off potential. The intensity of the incident radiation or light does not affect the stopping potential. It is not the intensity. If we make use of higher intense radiations or radiations of higher intensity, even then the stopping potential will be same. As you can see here, we have this graph for the different intensities of light, L1 and L2, where L2 is higher than L1. But the stopping potential for both kind of radiation means of different intensities, the stopping potential is same. We represent this stopping potential by Vs, or in some books it is written as V naught. So there should be no confusion in that. So this is the second observation that has been made in photoelectric effect. Let us move ahead. Okay, so it has been observed that the frequency of incident radiations, how it decides the photocurrent. Now if we keep the intensity of the incident radiation to be fixed, we are not changing intensity, we are using the radiations of same intensity but different frequencies. So the photoelectric current, it has been observed that the photoelectric current does not change with the change in the frequency. For all frequencies of radiations, we have same value of saturation current. Here in this graph, we have the radiations of different frequencies, nu1 and nu2, where nu2 is higher frequency than the nu1, right? So even for the higher frequency, we have the same value of saturation current. So that simply means that the frequency of the radiation does not affect or does not have control over the current. There is another observation, the effect of frequency of the incident light on the stopping potential. So if we, with the different frequencies, if we check the effect on the stopping potential, it has come to the observation that a radiation of higher frequency, it will have a higher stopping potential. The stopping potential for the radiation of higher frequency will be higher, right? And for the lower frequency radiation, the stopping potential will be lower. So that means higher the frequency, higher is the stopping potential. So this is the next observation that has been made here in the photoelectric effect. And last and very important observation that has been made is that there was no photoelectric effect below some certain frequency of the radiations. So it has been observed that the stopping potential, right, is plotted against the frequency for different frequency, and we have plotted the graph with the stopping potential. So it has been observed that below this frequency, this is the frequency of the radiation below which there was no photoelectron which was emitted and which needed to be stopped. So for this, the stopping potential is zero. So for this frequency, the stopping potential is zero. So that simply means that below this frequency, there is no emission of electron which takes place. Only the emission which takes place is beyond this frequency, or we can say at this and beyond this frequency. So we need the radiation of some certain minimum frequency with which the radiation can be emitted. If the radiation has the frequency less than this value, then there will be no emission of the electrons. And this frequency below which there will be no emission of electrons from the metal surface in photoelectric effect, this minimum frequency, it is called as threshold frequency, right? Because at this frequency, from the graph it appears that there is no stopping potential, or we can say the stopping potential is zero. So zero stopping potential, that simply confirms that there has been no electron which is emitted out, for which we require the stopping potential to prevent it from reaching the anode, because there is no electron, so therefore there is no need for the stopping potential. Hence stopping potential is zero for some certain value of frequency. This frequency it is called as threshold frequency. So this threshold frequency will be different for different kind of metal surfaces. It depends upon the nature of the metal which we are using for the photoelectric effect. So where does this concept of threshold frequency comes? It depends upon the kind of metal we are making use of. And how does that explain it? For example, that for a particular kind of metal we have an atom at the very central core of which we have a nucleus, and the electrons in the outermost orbit, because the electrons in the atom are attracted towards the nucleus in their particular orbits. Outermost electrons, they are also have some attractive forces being faced from the nucleus, right? So that means these electrons require some sufficient amount of energy to overcome this attractive force of the nucleus and hence become free. Once these electrons gain this amount of energy, they just overcome this attractive force of the nucleus and become free. So that minimum amount of energy, remember what word I am using, the minimum amount of energy which is required by this electron to just overcome the attractive force of this nucleus, this minimum amount of energy, it is called as the work function of this we can say metal surface. So different metals have different we can say work function. So work function of a metal surface or a metal is nothing but the minimum amount of energy required to just eject out an electron from the metal surface. We have to just take an electron and just make it released and give it no additional energy. The purpose is just to make the electron free, that's all. So that minimum amount of energy, it is called as threshold energy. So when an incident radiation is of a frequency called as threshold frequency or higher than that, only then this electron will be able to gain that certain minimum amount of energy. If the frequency is less than the threshold frequency, the electron will not be able to gain sufficient amount of minimum energy called as work function equal to its work function, and hence will not be able to become free. So that is the understanding of threshold frequency. So in photoelectric effect, what has been observed, it becomes the laws of photoelectric emission or photoelectric effect. So these are summed up here. So let me just recapitulate them once again and just see. So very first law is that for a given substance or for metal, there is a minimum value of frequency of incident radiation called as threshold frequency, below which no photoelectron will be emitted out and hence no photoelectric effect or emission will take place. Whatever the intensity of the light may be, but if the frequency of the incident radiation is not at least equal to threshold frequency, no photoelectric effect will be there. So there exists some minimum amount of frequency which must be the incident radiation should have in order to cause the photoelectric emission. Second law of photoelectric emission is that the number of photoelectrons emitted per second, that is, or we can also call it to be the photocurrent, because number of photoelectrons per second, that simply means the charge per unit time, means photocurrent. Photocurrent is directly proportional to the intensity of the light, provided the frequency is above the threshold frequency. Of course, only then the emission will be there. And this photocurrent is proportional to intensity of the incident radiation. More intense the radiation is, more number of electrons will be emitted out per second, and hence more photocurrent will be there. This is the second law. Third is that the maximum kinetic energy of photoelectrons, it is directly proportional to the frequency, provided the frequency is above the threshold frequency. That means the emitted out electrons will have some kinetic energy. Look, the incident radiation have some kind of we can say energy which the incident radiation gives to the electrons, and with that energy the electron comes out from the we can say metal surface, provided the frequency of incident radiation is some certain value, at some certain minimum value threshold frequency or higher than that. So if the frequency of the incident radiation is sufficiently more than the threshold frequency, then of course the electron will be emitted out. But now the electrons gain when the frequency of the incident radiation is sufficiently higher than the threshold frequency, then the electrons gains the energy which is much more than the energy required to come out from the metal surface. So where this excess amount of energy is used, so whatever energy an electron receives from the incident radiation, a part of it is used in order to overcome the work function, and the remaining part of the energy received by the electron from the incident radiation of some certain minimum frequency. So the remaining amount of energy, it is used in the form of the kinetic energy of the electron. It is that energy which is converted as the kinetic energy of the electron, which exists as the kinetic energy of the electron. So it says that maximum kinetic energy of the photoelectron, it will depend upon the frequency of the incident radiation, and of course the frequency, it should be more than the threshold frequency. Another thing is the law of photoelectric emission is that the maximum kinetic energy of photoelectrons, it is independent of the intensity of the incident radiation. It has been become the law that intensity of the radiation does not decide what kinetic energy electron can have. So the kinetic energy of electron, it is not coming from the intensity of the radiation but from the frequency of the radiation. The next law is that the process of photoelectric emission is instantaneous. That is, it happens as soon as the incident radiation of some certain minimum frequency is incident. It does not take any we can say time lag. Photoelectric emission, it is one-to-one process. For every photon, let us not include this this point here, but we will discuss this law as later. So that is what photoelectric effect is. Its experimental setup, the various terms here, the existence of threshold frequency, stopping potential, photoelectrons, photocurrent, and all other terms which are related here. And we have observed all kind of observations which has been made in photoelectric emission, and based on these observations there are some conclusions which become the laws of photoelectric emission. Now in the next class we will try to explain these laws on the basis of first wave theory of the light proposed by Huygens, and then we will understand whether the application of wave theory of light is accurate or not. And then we will see for the other options which can explain these phenomena with higher accuracy. That's all about this class on photoelectric effect. Thank you.